So in this short video I'm going to briefly show you what happens when a binary search algorithm is run. So we need a set of values. Okay, so we'll fill this array here with a set of numeric values. And with a binary search, the values have to be in ascending or descending order, but they have to be sorted for the binary search to work. Okay, and with a binary search there are a number of variables in play. One is a pointer to the index of the lowest value in the array. One is an index pointer to the position of the highest value in the array. And a third is a pointer to the midpoint in the array. So what a binary search does is it takes an array, looks for the target value, and then drops one half of the list depending on where the target value sits, whether it's higher or lower than the midpoint. So let's show an example. So if we set the target to be 3 in this case. Okay, so our target's 3. We've got our low point, which is currently set to position 0. I'll draw it here. And our high point, which is currently set to position 0, 1, 2, 3, 4, 5, 6, 7. And I place it there. Then we can calculate our midpoint. Now the midpoint is an algorithm, or a sort of calculation, where you take the highest index and you add the lowest index to it, usually, and then you divide that by 2 and you get the midpoint. So in our example, 7 plus 0 is 7. Dividing that by 2 gives you 3.5, but you can't have a 3.5 index because that would be kind of somewhere here, somewhere here, and that would return an error. So you have to round it down or round it up. So the way that I write the algorithm is I always add 1 to the array, to the calculation, sorry. So we have 7 plus 0 plus 1, that gives you 8. Dividing that by 2 gives you 4, and this is index position 4. To make sure that you end up with an integer number and not a decimal, then it's a good idea to floor it. And in Python code, floor is the double slash. And that just removes all the decimal points, okay? That's just a little hint for you guys. So, if we calculate the midpoint to be 7 plus 0 plus 1 divided by 2, it gives us 4. So our midpoint is here. And then what we do is we compare the target to the value of the array at the point of mid. Okay, so is 3 equal to 8? No, it's not. So we haven't found our target. But now we can dispose of one half of the list by just saying, is the target higher or lower than 8? Well, it's lower. So if we know it's lower, we can get rid of 8 because we've tested it, 10, 12, and 15. And that significantly reduces the search space. And how do we do this? Well, we just move the position of high. So instead of high being pointer to position 7, high is now position 5. Position 5. It's pointing to the value 5. It's actually position 3. Okay, that's 0, 1, 2, 3. And then we recalculate mid again. So when we recalculate mid again, we have 3 plus 0 plus 1. Well, that's 3. Okay, we divide 3 by 2. We get 1.5, but we round it down. So our next mid, our second mid, is pointing here. Okay, because we're finished with this one. And that mid is position 1. Because 3 divided by 2 is 1.5, we round it down to 1. And we test, and we say, is target equal to the value at the index of mid, and it is, and so we found our match and we can stop. Okay. Now this isn't very useful, a binary search, for any search that's under about 50 items. Okay, it becomes significantly more useful the larger the search space. So if you're searching for through 1 million items that are sorted into order for a particular target, you're going to find that much more quickly than if you search for it using a linear search technique, especially if it's in the second half of the search space.